All right, so let's begin the second talk of the afternoon session. We're very happy to have Edgar Shaghoulian from UPenn talking to us about the central dogma and entanglement in D-star space. Over to you. Edgar, you're on mute.
Thank you. Sorry, I just reconfigured my computer, so some stuff is not the usual way. Anyway, yeah, thanks for the introduction and thanks for hosting this workshop. I'm going to be talking about something somewhat speculative, as sort of most formal things in cosmology are. It's based on these two papers that appeared late last year and early this year. And let me just kind of jump into the question that I'm going to be talking about. There we go. So first, let's just review what we think we know about black holes. And well, some stuff we pretty reliably know. So quantum black holes we think of as somewhat like a gas in a box. They have, in the sense that they have a temperature and an entropy. Okay, here are the formulas for the temperature and the entropy. And we've asked and continue to ask what the sort of atomic description is for these black holes. So Boltzmann provided the atomic description for a gas, which has a temperature and an entropy. And he explained the entropy as all the sort of ways you can reconfigure these atomic constituents while keeping fixed some macroscopic parameters. You sort of count those ways up, and that is related to the entropy of the system. So there's this idea, it's an old idea, but I'll give it the name, the black hole central dogma, which is that you could think of a black hole from the outside as being just like a gas in a box. It's just some quantum system. It has a Hilbert space dimensionality given by this formula, and it evolves unitarily. Of course, it's an open system, it's interacting with the environment, but it's otherwise a unitary system. And again, this is an old idea. It's called a central dogma because some of us believe that it's true, but we don't know that it's true for general black holes. We have evidence for it from various perspectives, but we would like to understand more about it. And some of the work that I'm going to be sort of inspired by in this talk is work from a few years ago now, which seems to suggest that the gravitational path integral shows you that the region beyond the event horizon of a black hole can actually be accessed from the outside. Okay, this is the idea of these wormholes or islands, which tell you that there seems to be some connection between the inside of the black hole and the outside of the black hole. This is going to inspire some of the questions that I want to think about in the context of cosmology. So here's a simple cartoon of a black hole's event horizon. Okay, here's us, the observer. The event horizon is this red dashed sphere. These arrows signify that space is collapsing inside the black hole. And here's some photon, which is trying to make it out to us, but it's not going to make it out to us, okay, because it's inside the event horizon of the black hole. Okay, cosmology is somewhat like the inverted situation, at least for an accelerating cosmology. You have cosmic event horizons. Okay, these event horizons surround you as an observer. And then there can be photons or particles that are so far away that the space is expanding sort of too rapidly in between you and the photon, and it's never going to make it to your eyes, to the observer. So in that sense, you have an event horizon that surrounds you. Okay, so this is the sort of first similarity between black holes and at least accelerating cosmologies, which suggests some connection between the two. But the connection goes further. Cosmic horizons have a temperature and an entropy as well, and the entropy formula is the same as the one for black holes, and they radiate. So you can ask, do they obey a central dogma? In other words, can you think of cosmic horizons as just some sort of a quantum system with some finite dimensional Hilbert space evolving unitarily by interaction with its environment? Okay, again, this is also an old idea. It was first kind of proposed and entertained by these authors in the early 2000s. But that's sort of the question that's going to motivate some of this talk, or most of this talk. And okay, you can discuss this question for accelerating cosmologies in general. I'm going to focus on, at least from the level of symmetries, what the simplest example is, which is global de Sitter spacetime. However, in the metric for at least part of de Sitter spacetime, known as the static patch metric, it's called the static patch metric because it's static and it's a time translation killing vector. There's no t dependence in the metric. And the temperature and the entropy of de Sitter space are given by these formulas here. Okay, the entropy formula is just the same as I've written up here, and here's the temperature. So I'm going to focus exclusively on de Sitter spacetime in this talk. I always like to paint a sort of cautionary tale when talking about this subject because it's pretty speculative. We don't know that much about quantum cosmology, and there's some reasons to doubt this similarity between black hole horizons and cosmic horizons. For example, we have very little microscopic support for the Gibbons-Hawking entropy of a cosmic event horizon. Okay, we have calculations in string theory which reproduce the entropy of very sort of special black holes by counting microstates. But we don't have any sort of single agreed upon computation like that for cosmic horizons. Okay, so that's the first caveat. Another caveat is the black hole horizon, we think, encodes the interior of the black hole. So you can ask about the cosmic horizon, which side does it encode? Does it encode the side you're on? Does it encode the stuff beyond it? Is it neither? Is it both? So that's something that we don't completely understand. The next thing is that the cosmic horizon is both more universal and more observer dependent than the black hole horizon. So what do I mean by that? By the universal part, I mean that you don't need to sort of excite the system to have a cosmic horizon. Black holes we think of, especially in ADS-CFT, is excitations above the vacuum. So you need to do something to get it. But in accelerating cosmologies, we have the cosmic no-hair theorems and stuff like that. It's sort of the vacuum state itself has horizons. The Bunch-Davies vacuum or the Hartle-Hawking vacuum in de Sitter space is just classically this geometry which has horizons in the future. So you don't need to do anything to the system to see the cosmic horizon. In that sense, it's more universal. It's more observer dependent because for a black hole, anyone who stays outside the black hole is going to share the notion of the black hole event horizon or their event horizon. Someone who jumps in will have a different notion of an event horizon. But for cosmology, different observers in different parts of de Sitter space will have different event horizons because the event horizons surround them. There's some Hubble sphere surrounding them. Okay, so it's more observer dependent. And in that sense, assigning some quantum system to it is a little funny. Finally, an important technical thing which we don't have in de Sitter space is that there's no asymptotic region at fixed time where gravity is weak. Okay, in ADS-CFT, this is super important. You can place boundary conditions at the boundary of ADS where gravity is getting weak. And that's how we think about the duality. In de Sitter space, back reaction on the system is always important. Since gravity is not weak anywhere at any fixed time, you don't have you don't have something to kind of anchor yourself to. And another comment, I bolded it here because I think it's a very important distinction in cosmology, at least in the way that I'm going to approach the problem, as a comment maybe for the experts, is this issue of overlapping encoded regions. So in the technology of using replica wormholes and islands, the statement that you sort of land on is that if you're outside the black hole and you collect enough radiation, then you could encode a piece of the interior of the black hole. Now, you can ask, is there a statement like that that's true in cosmology? If you're inside the cosmic horizon and you do something, maybe you collect some radiation, I don't know what. But if you want to make the statement that you encode what's beyond your horizon somehow, then you're going to run into the issue that two different observers in two different parts of the universe, if they both encode what's beyond their horizon, they could be encoding the same piece of space-time. So those regions can overlap. And that's problematic. The way we understand holography, at least in ADS-CFT, is through something called complementary recovery, which is that sort of independent pieces are not going to encode the same piece of space-time. If they did, you'd run into problems with cloning and things like that. So that's a comment for the experts. At the end, you can ask me about that if you want. But Adam Levine and I wrote a paper exploring this recently in the context of 2D cosmological models. And there are lots more. Often when I give this talk, people like to contribute their own reasons why this analogy is not very good between black holes and cosmologies and why cosmology is difficult. Let's just put those complaints in the ellipses. There are lots of reasons to be a little cautious. Okay, so I've aired my dirty laundry, which means I'm allowed to proceed. Let me just give a little bit of background in the sort of three dominant ways people have thought about this problem. The problem of thinking about holography for de Sitter spacetime. So here's a de Sitter spacetime Penrose diagram. Okay, it's a square. Up here is future infinity. It's a conformal boundary. Down here is past infinity. It's also a conformal boundary. These vertical lines are not boundaries. This is where space caps off. The time slices are spheres. And okay, I'll just briefly say that people have thought about the holographic dual as living in various possible places. The approach that's received the most attention is that the dual is located near scry plus and or scry minus. Okay, there's the approach of DSCFT. Another idea is that the holographic dual is located near the static patch observer. So the static patch metric, which I'd written before, is the metric that covers this triangle here. And there's an idea that you could think of the holographic dual as being located near the origin of the static patch, somewhere along here. Okay, you imagine carving out a little world tube, and you think about holography sort of relative to the observer. That's an idea that's been explored. I won't really get into the various reasons and motivations for saying these things, unless people want to know. But the final one, which was most pursued by Banks and Fischler, is that the holographic dual lives sort of near or on the cosmic horizon. Okay. The cosmic horizons are the dashed lines I drew here. I should point out that the second and third forms of thinking about holography are observer dependent. This one explicitly, it says near the static patch observer. So what observer you pick is going to enter into this holography here. But also this one, the horizon itself is observer dependent. Here I've drawn horizons that are appropriate for an observer who lives here and an observer who lives here. But different observers, one that goes through the middle, let's say, has a different cosmic horizon. So these two are observer dependent. This one is not, but this one sort of concerns itself with meta observables. It talks about stuff on scry plus, which no single observer can see. So you sort of have to pick your poison. Either talk about meta observables. This is kind of appropriate for thinking about us looking back at the inflationary era. When we look back at the inflation era, in some sense, we have access to a big piece of scry plus of the previous de Sitter space or quasi de Sitter space. So that one concerns itself with meta observables, which you might not have access to depending on the problem you're studying. These ones are observer dependent. Okay. In this talk, I'm really going to focus on the second and third ones. I'm not really going to focus on this DSCFT approach. Okay, I'll just blow through the review. I'm sure people already know. There's this nice technology I'm going to use, which originated in ADS-CFT, but we believe is more general. And it tells you that you could compute the entanglement entropy of the dual CFT by extremizing a bulk quantity known as a generalized entropy. So let's say you want to compute the entropy of the CFT, trace rho log rho for the density matrix, let's say of some region, let's say within this dashed circle here. So this represents the ADS boundary. This dashed circle is a region within which we want to compute the entanglement entropy. And the proposal is that you extremize this quantity, where the area is some surface you can draw. I've drawn it here in pink, which ends on this dashed circle at the boundary. And S matter is the entropy of the matter contained within that surface. Okay, so you extremize that. If there's more than one extremum, you take the minimum, and that's computing for you the CFT entropy. Okay. So there are two important pieces of physics that go with this computation, which I'm going to use as I go on. The first is the notion of entanglement wedge reconstruction. What this gives you is some idea of holographic duality for subregions. So it says that the data within this pink surface in the bulk is reconstructible from the CFT data within this dashed circle here. Okay, so it's some sort of subregion duality and vice versa, but we don't really have a complete non-perturbative understanding of the bulk, so we usually say it this way, that you could reconstruct the bulk from the boundary. And if that's true, then there's a basic sort of consistency condition that has to be true, which is known as entanglement wedge nesting. It says that the reconstructible region, which is the region within this pink surface, should grow as the CFT region grows. that makes sense. As you grow the CFT region, you have access to more information about the CFT. You should be able to access at least as much of the bulk as you could before. Okay, so that's a consistency principle that has to be true. And you can, it reduces to computations in classical or semi-classical gravity to see that that's true. Okay, any questions about nesting? It's going to be pretty important for the first part of this talk. Okay, in that case, I'll proceed. So let me sort of paint an analogy which hasn't really escaped anyone who's thought about de Sitter space, which is that it kind of looks like an eternal black hole space-time. So here's a de Sitter space Penrose diagram again with the horizons. It's a square. So is the eternal black hole Penrose diagram. So the Penrose diagram being the same means the causal structure is the same. It doesn't say anything about the geometry. In fact, the geometries are radically different. You have singularities down here and up here, whereas this classically in de Sitter space, the space is huge up here and down here. These are conformal boundaries. Okay. Now, in some of the computations of islands and accessing the interior of the black hole, it was useful to append these flat space regions to the ADS boundary. Okay, I've denoted them in gray because they're taken to be non-gravitating. Red represents a gravitating region. And if you try and do that in the de Sitter case, remember, this is not a conformal boundary, this line here. So instead, what you have to do is carve out some region near the origin and declare that gravity is non-dynamical there. This is a weird thing to do. Near the ADS boundary, gravity is really getting weak. So you can, it makes sense to kind of continuously go into a region where gravity is shut off. But gravity is not really getting weak near the origin of de Sitter spacetime in any sense. So this is a bit of a strange thing to do, but it's the lesson I want to draw from doing this, I think, is more general than this toy model. So if you're worried about this toy model, hold on to your worries until I get to the punchline, and then you can revisit it if you're concerned. But that's what we're going to do, just to be able to do a computation. And when computing entropies, it's often very useful to think about what entropy in the microscopic theory you're computing. Okay. In this case, we know what the dual theory is. At least we know structurally enough features about it. If this is, an ADS2 spacetime, these we often call the SYK or quantum dots. These are, you could think of as dual to the red region here, but now they're coupled to some semi-infinite region that hosts a higher dimensional quantum field theory, conformal field theory. That's what these semi-infinite lines are here. And since this is the eternal black hole spacetime, this is in the thermal field double state. So this left theory is entangled in the thermal field double state with the right theory. And in a picture where you have something like holography for a static patch observer, you would imagine something somewhat like this. It's similar to this picture. Now you don't have these semi-infinite regions, you have these finite regions because this gray region here is finite. And these two are in some sort of entangled state. They could be interacting or just entangled. I'm not going to really use anything about the interactions or degree of entanglement as I proceed. So that's sort of the idea of what something like this would look like. And okay, the first thing you compute seems promising. We know that the black hole entropy in the eternal black hole could be interpreted as the entanglement between the two sides. Okay, the way that works is you declare in the microscopic theory, you want to compute the entropy of one of the two complete theories. Okay, that's what these x's denote. That's the x's with the line in between them is denoting the region whose entropy I want to compute, meaning I need to trace out the left. The way that's done using the Ryuta-Kainagi formula or its generalizations is that you sort of extremize this left endpoint in the bulk. So it starts here, and then you look to extremize it. And a natural extremum is just the black hole bifurcate horizon sitting right there. And in fact, that's the correct extremum. And the entropy then becomes the generalized entropy, the area of this horizon, plus the matter entropy in here. But in any event, we see that the black hole entropy, the area of this horizon, can be interpreted as the entanglement between the two sides. Okay, either in the semi-classical description or in the microscopic description. And in the de Sitter case, you would land on the same computation, at least naively. You compute the entropy of one of the two sides, you have to do the same thing. You have to extremize the left endpoint. You again, by symmetries, have a natural extremum sitting right here, the ds bifurcate horizon. So you pick that up, and you find that the de Sitter entropy is interpreted as the entanglement entropy between the two sides. So it seems to have a similar interpretation, which is great. It's a nice way to try and interpret the de Sitter entropy. But it has a problem. As soon as you do a slightly more general computation, it has a problem. The slightly more general computation is to compute the entropy of a smaller region of one of the two microscopic theories, okay, which has a bulk interpretation of computing the entropy of some amount of the gray region and whatever quantum system lives here. Then when you extremize left endpoint, you get something that looks like this in the case of a black hole. Okay, it lives to the right of the bifurcate horizon. And this is good. This satisfies entanglement wedge nesting. You shrunk the region of the microscopic theory you're looking at, and therefore you shrunk the region of the bulk that you're able to encode. Okay, that makes sense. In de Sitter space, it actually goes the other way. If you shrunk the region of the microscopic theory you're computing, meaning the bulk computation is you take some part of the gray region and you extremize with respect to the left endpoint, you'll actually find that the extremal surface lives to the left of the bifurcate horizon. Okay, this violates entanglement wedge nesting. The way you can find this, by the way, and you can do this in general dimension, is by using strong subadditivity. In general dimensions, de Sitter is conformally related to flat space. So you can map the entropy of regions like this to the entropies of annular regions, the regions between two spheres in flat space. And strong subadditivity gives you some constraints on the flow of that entropy. Okay, and that's actually enough, that coupled with the classical geometry, is enough to argue in general dimension that the extremum is going to live to the left. You can't compute it exactly because we don't know expressions for matter entropies of CFTs in general dimensions. So you can't compute it exactly. In 2D, you can compute it exactly because we know the formula for 2D CFT matter entropy in general conformally flat spacetimes. And there you can get an actual formula for this left endpoint and see explicitly that it's on the left side. But in any event, in general dimensions, you can argue that it's to the left. And this doesn't make any sense. Okay, if you want to compute entropies this way, you really need with it the structure of entanglement wedge nesting. I mean, it's not absolutely necessary, but it's strange to imagine a situation where you compute entropies this way, but don't have entanglement wedge nesting. So this is a problem. So this is a problem. This doesn't actually make any sense. And therefore, our original computation, which picked up the ds bifurcate horizon as the entropy between the two sides, also doesn't seem to make any sense. Okay, so this seems very different than the black hole bifurcate horizon. So what went wrong here? Well, what went wrong is that, you know, these two diagrams look similar, and these are extremal surfaces, but as I said, the geometries are different. This black hole event horizon is, you could think of as what's called a maximin surface. In other words, it's a minimum in space. So imagine this time slice here, this t = 0 time slice. The area here is minimal, right? There's some wormhole which has its smallest size right at the horizon. And so it's a minimum in space and it's a maximum in time. The areas here are going to 0 here and here. So they're maximized right in the middle here. So it's a maximum in time and a minimum in space. The geometry of de Sitter is the opposite. Remember, the global de Sitter is some hyperboloid that kind of contracts at t = 0 and then grows again once you go to positive time. So it's actually a minimum in time and it's a maximum in space. Okay, it's the great sphere that surrounds you. It's this point here. You know, this sphere is here degenerating to 0 size, so it's maximal here. So this surface is a maximin surface, and that's actually crucial in, you know, proving and arguing that entanglement wedge nesting is true in examples in ADS CFT, using just GR and focusing and things like that. But if you use minimax surfaces, you would have the sort of opposite conclusion. So really what we did wrong is that we found a maximal surface instead of a minimal surface. and if you think about just a constant time slice. And a maximal surface is not a good surface to use for computing entanglement entropy. Okay. So that's sort of the lesson of the first part of the talk. The de Sitter horizon, you can't sort of naively use it in the same way as a black hole horizon because it's a minimax surface instead of a maximin surface. So any questions about that? Okay. In that case, let me proceed. Okay, so we ran into this problem where we considered holography kind of near the static patch observers. So we can ask about placing the holographic dual theory on the de Sitter horizon. This was the sort of in the list of 3 ways of thinking about holography. This was the 3rd way that you could think about it. And you're sort of immediately faced with the question of which side of the horizon does this holographic dual theory encode? You know, in ADS-CFT, when we place the holographic dual theory at the ADS boundary, there's only one side of the ADS boundary, and that's the side that is encoded. But if you place the dual theory on the de Sitter horizon, there are 2 sides to the de Sitter horizon. So you have to ask which side is encoded. I think there's an analogy with ADS-CFT, which to me sort of makes it clear in a way what the answer is supposed to be. And to see that, let's go back to the example of an eternal ADS black hole coupled to these flat space regions that we use for various black hole calculations. As I said, the microscopic description is, 2 quantum systems coupled to semi-infinite higher dimensional theories in the thermal field double state. You could ignore this rightmost column. This is the doubly holographic picture for people who are familiar with it. You can ignore it. So we can actually modify this example. Okay, one way to modify it is instead of taking these semi-infinite regions, you take these finite regions. So let's start in the microscopic description. Instead of having a semi-infinite CFT region, you take a finite region and then you couple it to another pair of quantum systems, the blue ones. Okay, and these all together are in the thermal field double state. The bulk picture of that is now that you have 2 ADS regions. Penrose's diagram is periodically identified here. So you have the red eternal black hole and the blue eternal black hole, which are dual to the pair of red and pair of blue quantum systems. Okay, now that you've done that, it's sort of clear what you can do. You can sort of shrink this region to arbitrarily small size. Okay, and then you'll basically have just the red and blue quantum systems interacting with one another. Red and blue make purple. So you have 2 quantum systems in a thermal field double state. And now each of these quantum systems lives at either this ADS boundary or that ADS boundary. And now there's space-time to both sides of the ADS boundary. Okay, so while usually in ADS-CFT we have an ADS boundary with space-time to one side, you could construct these examples where you have an ADS boundary and it has space-time to both sides. And if you ask the question, which side of the ADS boundary is this purple holographic dual encoding? Well, it's both sides. At least it has the potential to encode both sides. Okay, and practically speaking, in computing entanglement entropy, when you go to find extremal surfaces, you want to find them on both sides of the ADS boundary. So motivated by that, I'm going to declare that we do the same thing in de Sitter space. So I'm going to declare the microscopic theory lives on a sort of pair of horizons. So here we've sort of gauge fixed to a pair of observers. And the holographic dual theory I'm going to declare is going to live on a pair of horizons on a global slice. So here's a global slice. It looks like this. It's a sphere. The horizons are to the left and right of the middle because we're at some positive time. And I'm going to call these regions the left and right interiors and this region the exterior. And pictorially, this doesn't mean anything here. It's just helpful to think of them as 3 separate regions. So often I'll break them up into 3 different regions in this way. Okay, HL and HR just to note the left and right horizons. So what's the proposal? Well, there are 2 proposals one could think about. The one I just motivated is to extremize, if you want to compute, let's say, the entropy of the left horizon on both sides of the horizon, in the left interior and the exterior. Okay, that's what Lenny and I called the bilayer proposal. It's called bilayer because in a bit thread formulation of this proposal, there are sort of bit threads emitted on both sides. So it's as if there are two layers, but it's just the name. Lenny had a separate proposal, which is to only extremize in between the two horizons. Okay, and this we call the monolayer proposal. And I'm going to explore both of them in the rest of the talk. The one thing I want to point out, which is nice about the bilayer proposal, is that you have a natural notion of an entanglement wedge. If you compute a surface to the right and a surface to the left, then you'll have a natural enclosed region of the gravitating spacetime, which means that there's a natural quantum extension of this formula, because the quantum extension says that you should add in to the area of the surface the matter contained within the surface. And to have, topologically for that to work, you really need to have surfaces to the left and the right. There can still be a quantum extension in the monolayer proposal, but it's not going to be obvious what the guess for that should be. Okay, this might seem a little funny, so I'm going to work through some examples, and then I think it'll become clear how the two proposals work. Let's start by computing the simplest thing we can compute, which is the entropy of one of the two horizons. So we've taken this global time slice at some finite positive time, and we want to ask about the entropy of the left horizon. So I'll compute using the bilayer proposal first, and then I'll compare to the monolayer answers at the end. Bilayer says that you should find an extremal surface to the left and the right of the horizon. So let's first find an extremal surface to the left. Well, to the left, we have the trivial surface. Okay, you can imagine dynamically, you start with a circle on the sphere, and you want to minimize it. Well, it's allowed to shrink and slip off and go to the pole of the sphere and give you zero area. Okay, so you don't pick up any area from that surface. But now when you extremize in the exterior region, the area is getting big out here. So the surface doesn't really want to go anywhere. It's going to sit right at the horizon. So when you add up those two answers, a over 4g plus 0, that gives you a over 4g. And you recover the entropy of the de Sitter horizon. I mean, somewhat trivially, because you anchor things there. But nevertheless, you get the area divided by 4g. And from the bilayer picture, you see that the entanglement wedge is the interior of the horizon. So the holographic dual theory that lives on the left horizon seems to encode the interior of the left horizon. That's the answer you seem to land on. And you don't have the problem we had in the first part of the talk. There is a way to reformulate this as a maximin prescription, which tells you that the horizon is actually a maximin surface. Calling the surface maximin or minimax is somewhat a function of how you land on it. It's not just a property of the spacetime. So in this sense, you could think of this as a maximin surface, which means that you don't expect to run into problems with entanglement wedge nesting. And in any example I go through in this talk, you'll see there are no problems with entanglement wedge nesting. Okay. Let's do something a little bit more involved. Let's compute the entropy of the union of the two horizons. We expect to get 0 because the global state we're talking about on de Sitter space is a pure state. So let's say we're in the Hartle-Hawking state. So entropy of a pure state is 0. So and the full holographic dual lives on the union of the two horizons. So if you compute all of the entropy, you should get 0. The way you see that is simple. Now you need to compute for the left and right horizons. When you extremize to the interiors, you're going to find that it slips off and gives you the 0 area surface. And when you extremize to the exterior, since you have surfaces on the left and right horizons, you're again allowed to pick a trivial surface in the middle. That satisfies the homology constraint. Another way to think about it, these surfaces can come together and kind of annihilate and give you a trivial area surface. So you find that the entropy is 0, and the entanglement wedge is the entire space-time. Let me emphasize that this computation, computing the entropy of the union of the two theories, is exactly like computing the entropy of the union of these two purple theories. You expect to get 0 because they're in a pure state. And the way you see that in the bulk is that you're allowed to pick the trivial surface in the red and the blue regions. Okay, so it's a lot like this case. And the monolayer theory gives you the same answer, same numerical answer for the entropies. And the reason for that is that the only difference in the monolayer and bilayer proposals is that in the bilayer case, you have to extremize in these interior regions. But those extremizations never gave you anything that contributed to the entropy. Okay, the only case we had something non-zero was here, and that came from the extremization in the exterior region. While this seems trivial, I do want to emphasize that it was actually pretty tricky to get this A over 4G, in the sense that, you know, people tried to anchor things to the horizon before and compute the entropy of the horizon. And actually what you naturally find on, because the natural thing is to only extremize in the interior, is that you get 0 for the entropy of an entire horizon. So it was crucial to add in this thing of extremizing to the exterior of the horizon to actually get A over 4G once you consider the full horizon. Okay. You can also do this for the Schwarzschild black hole in de Sitter spacetime. So here I'm going to consider the geometry classically. Okay, quantum mechanically, it's not stable. But classically, you have a solution that looks like this. The topology is different. So here's the de Sitter region, it's inflating. Here's the black hole region, it's crunching. And the Penrose diagram is periodically identified. Okay. And now I won't really go through it, but you can do the same sort of computation. You could compute the entropy of a left horizon. What you'll find is the area of the cosmic horizon plus the area of the black hole horizon. That's this tiny blue circle here. And you'll find that the entanglement wedge is a region between the black hole horizon and the cosmic horizon, which is what you might expect. And if you want to compute the entropy of the union of the two horizons, you again find that the entropy is 0, as it should be, because you're computing the entropy of the full system, which is in a pure state. In this case, you see that you have to do a joint extremization, meaning you can't extremize to the left interior and the right interior separately. If you did that, you get like 2 copies of this blue surface. You see that it's just one overall extremization you do, and then they can kind of come together and annihilate. So again, you get the expected answers, and the monolayer theory gives you the expected answers as well. In these cases, it's supplemented by a proposal, which is you don't only extremize between cosmic horizons, you extremize between any pair of horizons. So in particular, if you have black hole as well, you also extremize between the black hole horizons, and that's what gives you this A black hole over 4G. Okay, so the 2 proposals give you answers that we expect to be true in a quantum theory of de Sitter space. So why did I bother kind of distinguishing them and going through this song and dance? It's because there's one case where they seem to give you different answers. Okay, and the one case, it's not clear that it's a totally reasonable thing to do. It's actually, my guess would be that in an actual holographic dual, it'd be related to the type of things that Sumit was talking about, computing something like target space entanglement. Or in other words, kind of like trying to chop up the internal space in ADS-CFT. It feels a little bit more like that, because what we're going to be doing is dividing the horizon into pieces. So far, I've only computed the entropy of a full left horizon or the union of the full left and full right horizons. But you could ask about a subregion of the horizon. Okay, and in terms of the holographic dual, okay, we don't know what that means, but the natural guess, well, a general guess is that it's some subdivision of the holographic degrees of freedom. It's probably not a geometric subdivision, again, like in the target space entanglement case, but it's some subdivision. But let's compute it. It's a well-defined bulk thing to compute. And in the bilayer proposal, what you see is a little troubling at first. So let's say we're computing the entropy of this red region here. Okay, the geometry I've drawn in a slightly funny way here, but the answer is correct. If you want to extremize to the interior, the surface is not going to want to go anywhere, actually. It's going to sit right at this horizon. And similarly, if you extremize to the exterior, it's not going to want to go anywhere. It's going to sit right at this horizon. So you're going to get 2 times the area of the region whose entropy you're computing for the answer once you do the extremizations. That's bad because at the halfway point, it's going to exceed, it looks like it's going to exceed the area of the full horizon because you're going to have 2 copies of 2 times half the horizon. And natural guess for a central dogma for de Sitter space is that the Hilbert space of the horizon theory has e to the a over 4g Newton number of states. So we don't want to exceed that by computing an entropy. We can't exceed that. That would be inconsistent with the assumption. This is somewhat like what happens with a black hole. You stay outside a black hole, you collect all the entropy, you can collect all the radiation, you compute its entropy, and you see that at some point, the page curve is threatened. It looks like the entropy of the radiation is going to exceed the A/4G of the black hole. What happens in that case is a phase transition. A new surface kicks in. This is the island surface. And that brings the entropy down to be consistent with the central dogma. And what we see here is a very similar sort of thing. Exactly at the halfway point, the surface on the inside is allowed to flip around and live on the complement of the horizon. So then you have the piece of the horizon's entropy you're computing plus its complement. The total entropy is exactly A/4G Newton, up to G Newton to the 0 corrections. And again, that's exactly what happens for a black hole. The entropy saturates, the entropy of the radiation saturates at A/4G Newton plus subleading corrections. So this island-like transition at the halfway point seems to save the central dogma. You might be a little bit worried though, because we like to think of de Sitter space as a thermal system. And the entropy of a subdivision of a thermal system looking like this is a little bit weird, right? Thermal systems have extensive entropies. So we don't expect, as we increase the subset size of the system, to have this kind of sharp kink-like feature. And if you're worried about that, you would be somewhat more pleased with the monolayer answer in this case, which, as I promised, is different than the bilayer answer. The monolayer answer doesn't have this interior surface that I drew here. It just has this exterior one. So it just grows as a fraction of the horizon size whose entropy you're computing. So it just grows linearly all the way to the A/4G Newton. This is more like what you expect for the entropy of a thermal system. It's extensive. But now I just want to take a moment to say that even though this is what you expect for a thermal system, it might not actually be what you want for de Sitter space, or really any sort of large N holographic thermal system. And the reason for that is that large N systems are not traditional thermal systems. Okay, we think of the large N limit as similar to the thermodynamic or large volume limit, but they're really not the same. Okay, and it's simple to see why. We'll see in a second. But first, I'm going to say the reason, I guess one way to think about the reason why they're so similar, I guess one way I like to think about it is that holographic CFTs, at least the ones dual to Einstein-like theories, have higher form symmetries coming along for the ride. And in particular, they have a particular pattern of higher form symmetry breaking. And this particular pattern of higher form symmetry breaking through this mechanism, you can argue it makes them look a lot like large volume thermodynamic limits. So what do I mean by that? Well, the simplest observable you could try computing is the entropy of the system. Okay. The entropy of an extensive system, so in the infinite volume limit, or let's say the infinite temperature limit in a CFT, those two things are the same, is this. Okay, you just have the volume law scaling. But in a traditional thermodynamic system, as you back away from the large volume limit, you have sub-extensive corrections, right? Generally, you could have an entire function of v times t to the d minus 1. That would be dimensionally consistent for a formula for the entropy. And if you compute in various theories, you do have a non-trivial function. This is only the answer as t goes to infinity. In holographic systems, this is the answer not only at t equals infinity, but t above the Hawking-Page transition temperature. Okay, you immediately get this extensive scaling. This is for CFTs compactified on tori. Let's say if you want, you can just take a CFT2 and just have the CFT on a circle. So this is weird. You can ask where the hell are all the subleading corrections? And one way to understand why they're not there is these higher form symmetries and the particular pattern of their breaking. And this is true not just for the entropy. You could compute thermal correlation functions, and you'll also see that there are no non-trivial finite size corrections. So that makes all the answers look like they're at infinite size, because all the finite size corrections are kind of trivial. So it's true for many observables, but it's not true for all of them. A simple one that I'm sure many people are familiar with is to compute the entropy of a subregion of the CFT in the thermal state. So here's the ADS boundary. Here's a black hole. And we're in the thermal state here. And we want to compute the entropy of some region R, which we take to be bigger and bigger. So initially, we just pick up the UV answer. We don't really see the black hole. We don't feel its effects. But as we make the region bigger, we start feeling the black hole. So it looks like this starts hugging the horizon a bit. And then there's a phase transition, again, an order 1 fraction of the system size, where you flip to this surface union one that hugs the black hole horizon. And then as you increase R further, this region shrinks to 0 size. So you end up tapping out the sort of thermal entropy of the system at a fraction of the system size. Okay, this is not what would happen in a traditional thermodynamic limit. Again, this phase transition, order 1 fraction of the system size, is a lot like this phase transition from red to blue. Okay, and this is indicating to you that large N systems, even though they behave like large volume thermodynamic systems, you can compute simple things like the entropy of a subregion, which tell you that it's not. If you wanted to be in the thermodynamic limit, what would you do? You would take T to infinity. That would make this black hole very, very, very large. It would basically sit right near the horizon. And then this transition will be pushed to arbitrarily late times. You would actually just see a linear growth in the entropy in that case. So you still need to take the large volume limit if you want to see actual thermal extensive behavior. And my argument on the slide is that de Sitter space is a little bit more like this case. That's one way to think about it, that it could be more like this case. And that's why you don't get a thermal extensive answer, because it's a large N system, not traditional thermodynamic system. It'd be interesting to understand how this connects to, there's recent work by Witten and collaborators saying that at least semi-classically, you could think about de Sitter space as being at infinite temperature. Those sorts of arguments, if they're true sort of non-perturbatively, would give support for this kind of entropy curve, actually. So the jury's still out. I mean, we would like to understand this better. But this is one reason to think that all hope is not lost with a curve that has a sharp transition, because that's what we actually see in like ADS CFT. Okay, that is just some general support for the idea that the bilayer curve is not preposterous. But now we'd like to write down a simple toy model that reproduces a curve that looks like this. Okay, this sharp one. I mean, the one nice thing about this sharp curve is that it's very constraining. It's hard to find a theory that has a curve that looks like this. The monolayer curve is easy to write down a theory that looks like this. Take any theory you like and put it at infinite temperature. Its entropy curve will look like this. So in that sense, this curve is more of a constraint, if it's actually correct, on looking for a potential dual theory. So I'll write down a simple toy model which realizes that curve. It's not really what we want because it's not a large N system. And part of how it reproduces the curve is somewhat trivial. And it's this system. You have 2 qubits. It's what's called the Heisenberg antiferromagnet. So J is positive. And here's the Hamiltonian. And you could compute the entropy for 0, 1, and 2 qubits of this system. And if you do it at t equals 0, what's the state at t equals 0? You're in the spin singlet state. So 0 qubits, well, that always has entropy 0. 2 qubits, since you're in a pure state, has entropy 0. And 1 qubit, this is 1 qubit of a Bell pair, it's going to have entropy log 2. Okay. The infinite temperature answer is going to be the extensive linear curve that we expect. 1 qubit has log 2, 2 qubits has 2 log 2. Okay, you look at these curves, you might think, if I vary the temperature, maybe I can get one that kind of flattens out like I want. You might worry that the entropy of 1 qubit shifts, but actually there's an SU2 symmetry in this problem which fixes the entropy of 1 qubit to be log 2. So at any temperature, the entropy of 1 qubit is log 2 due to this symmetry, which means that there's definitely a temperature in between infinity and 0 where you get a curve that looks like this, the bilayer curve. Okay, that temperature, you can compute it, it's roughly 1.5 J. Okay, this of course is not a great reproduction of the bilayer curve because we don't actually have any data in these blue regions here. What we want is a large N system which really has non-trivial data that has this sharp transition that goes along here. But this is just to indicate that you can have entropy curves that, at intermediate temperatures, which have these kinds of still somewhat sharp transitions. Okay, I'm nearing the end, so let me just kind of summarize and point toward what I think are interesting future things to think about. So one of the main points I wanted to make is that the cosmic horizon is actually very different than the black hole horizon, in a sense that we can think about more precisely in the days of entanglement entropy and ADS-CFT, which is that it's a mini-max surface instead of a maxi-min surface. So it doesn't naively work as a quantum extremal surface. There are other ways you can use it, like I did in the second part of the talk, where I anchor to the horizon, which sort of don't run into these issues of it potentially being a mini-max surface. But one has to be careful about that. So, it sort of made up this rule in the second part of the talk of anchoring to the cosmic horizon, anchoring the surface of the cosmic horizon, saying the holographic dual lives at the cosmic horizon. Now, there are lots of reasons that's a little confusing to think about. The cosmic horizon is observer dependent. How do you define it in a different variant way? I mean, the horizon also moves, it reacts to matter. So, there are all these questions you can ask. So a simpler place to try and probe this is try and anchor surfaces to a black hole event horizon and ask, does that make sense? This is under a little bit more control because you can embed this in ADS-CFT, where we have a better idea what's going on. And so I think that may help understand a little bit whether this proposal makes sense and to sort of disentangle a little further the bilayer and monolayer proposals. Another question I'm curious about is more general cosmologies, like the one we live in, the one that begins with like a Big Bang. There isn't an obvious way to encode them by a pair of horizons. Okay, I mean, the global Penrose diagram of de Sitter space is a square, so it's natural to pick a pair of horizons. Moreover, in that case, there's a simple argument why you might have something like a central dogma. So as usual, it's confusing to think, how can this finite area encode this humongous inflating space beyond it, basically an infinite amount of space beyond it? And in global de Sitter space, there's a natural answer. The natural answer is that global de Sitter space is effectively a bouncing cosmology, right? Past infinity is huge. It contracts to minimum size at t equals 0, and then it grows again. So if you fix to having a global de Sitter geometry, that means that you did not put too much matter in the past. Alternatively, you can't have too much matter in the future, because if you rewound that to t equals 0, it would end up crunching and forming a singularity. So there's a just pure energetic limitation on how much stuff you can put in de Sitter space. And that is one way to understand why something like the central dogma can be true, why you have a limitation on the number of states you could have in an infinite amount of space. More general cosmologies that begin with the Big Bang, there's no such argument like that, because you can put as much stuff as you want at the Big Bang, as far as we know. There's no way to control the calculation. So understanding how encoding or holography work there, I think, might be sort of radically different than the case of global de Sitter space. And the most important thing, because this what I talked about is speculative, is to write down a microscopic model which matches some of these features. In particular, the feature I'm imagining is this bilayer curve for the entropy. I mean, if you wrote down a microscopic model that you had some other reason to believe might be relevant for de Sitter space, and it spat out this entropy curve, I would find that pretty compelling, because this is a very sharp feature. So that, I think, is one of the most important things that I'm currently thinking about. And with that, I'll stop here and take any questions in the last few minutes. Thanks.